Here is our next revision session, and it's based on radioactivity. And it's one of the ones we did most recently in class, but it's a very big topic. I'm going to try and break it down into manageable little chunks for us. So first of all, we're going to start with the model of the atom and why does it look the way that it does. We do need to understand a little bit of history, and that being the plum pudding model is the model of the atom that was around, let's just say, just before around the 1900s. And that then changed into the Rutherford model of the atom, which is the same model that we use today, pretty much. Now let's just remind you of what the plum pudding model was. Essentially it was saying that there was an atom, and people did realise that things were actually brought down into small blocks of matter, atoms, and then in there, interspersed, are electrons. And that was the model up to about 1900. And then Rutherford came along and suggested this new idea. And his new idea was this. You had a very small, dense nucleus. This is a small and dense nucleus. It was positive in charge, so it had a positive charge. And these electrons occupied this cloud around the outside. And compared to sizes, this was incredibly small, very, very small, compared to the width of this atom. So the Rutherford model of the atom, nucleus with electrons floating around the outside. Now the reason why this is taught so much at school is because it brings to light this idea of how science works, how we move from one idea into the other idea. And the one that made the experiment that drove us from one model to the other model was called the Geiger-Marsden experiment. Okay. And what they did for the Geiger-Marsden experiment was that they shot this newly discovered stuff called alpha particles, which we'll come on to in a minute, but they shot these alpha particles through gold foil. And what they were expecting was a nice, even distribution. So this was the expectation, let's call it. I'll roll that down here, expectation. But what was discovered was, in actual fact, most go straight through. So this was discovered. And it was identified by using this screen. So it was a screen that was surrounding the apparatus, and this screen continued all the way around, dot, 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 all the way around there. And it every time one of these particles struck the screen, there was a flash of light. They call it a scintillation of light. And the people essentially just sat around this screen and looked at it and saw where the flashes were. And they were expecting a nice, in a certain time, a nice even distribution of flashes. However, most of it went straight through. And even more surprisingly, some of it bounced back through large angles. Okay, so why on earth did that type of discovery therefore yield this whole new model of the atom? Well, this is the reason why. The first finding was that most went straight through. And that suggested that actually the majority of the atom was empty space. Or, indeed, that there was something very, very small in the centre, but it was so small that it didn't deflect the alpha particle at all. The second point was that some deflected through huge angles, so you had large angle deviation. And that implied two things. One, this deviation was caused by the positive alpha particle repelling something positive in the nucleus. Okay, and the second thing was that in order for this bounce, I say bounce, in order for this repulsion to have occurred, you must have a very, very dense, small, because it didn't happen very often, nucleus. So those are the two important points. Most went straight through. Some underwent these large deviations of angle. Most going straight through means it's empty space. Let's bring ourselves back up to this model here. So most of this is empty space. Some of them bounced at very big angles, implying that the positive alpha was repelled from this nucleus, and that all of the mass of the entire atom was concentrated inside this small little dense ball. So Rutherford inferred that those must be the conclusions and then came up with this model of the atom here. Okay, so that's a really important idea, the Geiger-Marsden experiment. And it shows how science develops through having a model which doesn't stand up to experimentation, and so therefore you have to build a new model and keep testing the new model. And we keep testing this model and it works. Okay then, so now coming on to a bit of chemistry, we're going to deal with the notation. So all of these atoms in the periodic table are going to be presented with, let's take one example, are going to be given a name. You're going to have a number at the bottom and a number at the top. I know this is chemistry, so we can be quick, but this, in effect, is the name. The 3 at the bottom are the number of protons. The number at the top is the number of protons and neutrons. Okay, and we usually give it this general description of X, A, Z. Proton number, atomic number, element name. Now, bearing in mind, these are the two things you ought to bear in mind. If you've got a different number of protons, the number of protons defines the element. You cannot get the same element with a different number here. Each of these numbers discretely link to a different element name. So the number of protons, or the atomic number, defines the element. However, you can have varying atomic masses. And they are called isotopes. In other words, if you have a varying atomic mass for the same number of protons, you must have a varying number of neutrons. Let me give you an example of that. Uranium-235 92, and uranium, it must be 92 if it's uranium, 238. So those are your two isotopes of uranium. This one, of course, has 3 more neutrons than that one. Okay, so you need to be able to and comfortable talking about isotopes. Now, what happens if it has an excess number of isotopes or a decreased number? So with a different number, of neutrons, okay, that causes instability. Now, we don't need to know why it causes instability, but there are all the elements of the periodic table, and they are often written down as the stable ones. In this case, that is the stable version. And the further away from this stable ratio, which is not one that you can work out, but it's just given, the further away you are from that stable ratio, the more likely it is to become unstable. And if it becomes unstable, what does that mean? Well, instability means it wants to start to become more stable. And if it wants to become more stable, it has to start spitting bits out of its nucleus. So what could we see there? If the more unstable, the more likely to give off radiation. That's another thing you need to remember. Now, where does it give off radiation? Well, if this is our tiny nucleus, and these are our electrons floating on the outside, if it's unstable, or unstable, then the nucleus gives off the radiation to try and be more stable. Hence, a nuclear process. It's nuclear because it comes from the nucleus. And I hope it makes sense to you. We say it can do this in one of three ways, either by alpha, by beta, or by gamma emission. Only one of those three. You can't just spit out a neutron or spit out a proton. It could spit out an alpha, a beta, or a gamma only. So let's talk about what the alpha, the beta, and the gamma are. Okay. Alpha particles, or given the term alpha, in effect is a helium nucleus. And when I mean by helium nucleus, I mean that means the helium atom, but without any electrons. In other words, it is merely 2 protons and 2 neutrons. There we go, that's an alpha particle. Okay, what about beta particle? Well, in essence, this is an electron on its own with a high kinetic energy. It's moving very, very fast. I often give it the symbol like this. It doesn't have any mass because electrons have very, very negligible mass to non-existent mass, but it has -1 of a charge. Electrons are negatively charged. So it is just an electron moving with lots of kinetic energy. And the third one, gamma, given the symbol gamma, is an electromagnetic wave of high energy. I don't know if you remember the electromagnetic spectrum, but gamma sits right at the one extreme. It's very, very high energy. But because an electromagnetic wave, it has no mass and it has no charge. It's just merely gamma. Electromagnetic wave. Okay, but how do they affect the nucleus when they're actually given off from the nucleus? Well, let's take the example of uranium. Uranium-92, 235, the unstable one. Because it's unstable, it will spit out an alpha. So we know what alpha is. It's 4-2. It's got 2 neutrons and 2 protons, hence 4 nucleons and 2 protons to it. So what does that leave us with? Well, if you've managed to take that off this element here, then what you're left with is something with 90 protons. These must add up on both sides. And 231 nucleons. And I know this is thorium, but you would have to look that up on a periodic table. Okay then, right, let's try it. So that's fairly straightforward. In other words, you have whatever element you start with, and in getting rid of an alpha particle, you're then left with something with 4 less nucleons and 2 less protons, and this is a new element. Okay, what about beta? Because that's a little bit more complicated. Let's go for carbon-14. I know that is 6. And let's say that gives off a beta particle, which is -1 beta. Then what that leaves me with is this must be equal on both sides. I must have 7 protons and 14 neutrons. Now I know 7 is nitrogen, so I know that becomes nitrogen, but it doesn't really make sense. Let's look a little bit more closely at what's actually happening. This is alpha and this is beta. What's actually happening? How does this electron pop off? Because remember, in my nucleus, my atom, it's not an electron that's popping off from there. Something's happening deep inside the nucleus. What happens inside the nucleus is, I'm not going to have time to draw all of these, however, let's imagine I have three, well, the dark ones here are protons. Then what takes place is, one of those neutrons, let me just draw in the protons, here comes the neutrons, one of those neutrons turns into a proton, and in doing so it shoots out an electron. Of course, the proton is retained again inside the atom, so therefore you've lost a neutron but you've gained a proton, so actually the weight, or the number of nucleons, the change in the number of nucleons is 0. You don't get a change because you've lost a neutron but you've gained a proton. However, there is a significant difference in charge. Because no charged particle is turned into a positively charged particle, it gains a charge. And so therefore that's why beta decay can confuse people. Remember, it is not an electron that's shot off from the outside of the atom. A change happens inside the nucleus, where a neutron goes to a proton and then the electron is shot out at high speed. Okay. And then very swiftly, I suppose, there's gamma. I suppose what you could say is, go with carbon-14. It's an excited state, which means that it's probably a little bit more information they need to know. However, what happens is inside the nucleus, some of these change position, and in changing position they release energy. No change actually occurs with the atom itself, other than this gamma particle is shot at. Okay then, so that's the radiation type. Well, how do you detect, well, what are the properties of the radiation? Well, first of all the radiation does, a use and a danger, is that it ionizes matter. And what do I mean by ionize? Well, it means that if you have an atom, and let's say alpha's coming past, it has the ability to knock off an electron and therefore ionize the matter. That alpha particle then carries on, but I'm going to draw it with a less of an arrow because it's lost some energy in kicking off that electron, and then it might do another kick off electron, and the alpha then moves on a little bit, but it's lost its energy, a bit more energy, and then it kicks off another electron until it stops. So it ionizes as it goes. Now, what you need to know about alpha is highly ionizing. And not a large part because it's quite slow, so it stays around this area, so it's got more likely to kick off electron. And also it's 2+ charges. So therefore it's very charged, so it's likely to do something to other charged particles. What about beta? Well, beta is moderately ionizing, not least because it's quite fast, so it doesn't stay around very long, and it's only -1 charge. Okay, and gamma, of course, is, I was going to say not, well, let's just write not very ionizing, because it's very, very fast and there is no charge to it at all. It's electromagnetic wave. So when we're talking about this ionizing, remember I said as it kicks off electron, it loses a bit of energy, it loses a bit of energy, it loses a bit of energy. If it's highly ionizing, then it's going to lose its energy very, very quickly. Moderately ionizing, it will lose its energy a little less quickly, and if it's not very ionizing, it won't lose its energy very quickly. So therefore what you have is, you have the alpha particle doesn't go very far, beta goes a bit further because it's not losing its energy as much, and gamma doesn't lose much energy, so it's very penetrating. So we talk about this as either the range or the penetration. How far does it move through matter? The more ionizing it is, the less the range. And we talk about penetration. We identify it with the minimum material required to stop the particle. So with alpha, we can have a few centimeters of air is good enough, or paper will stop it, along with everything else, but those are the minimum requirements. Beta, a few centimeters of metal. Gamma, meters of concrete or lead. So it requires quite a lot to stop gamma, but lead is able to achieve that. So if you were setting up an experiment, for instance, and you had to try and determine what was coming out of a source, alpha, beta or gamma, then what you might do is, let's just say we had a source shining off radiation, and what you do is you'd place in between different types of material to block it to see how much managed to get through the material. For instance, if you put beta in there, I mean, you could, and bear in mind when you're doing this experiment, you might get a decrease in the signal. And if there was a decrease, that suggests one type of radiation is removed. Of course, you can have one source equals more than one radiation. You might have an alpha emitter and a gamma emitter, for instance. Okay. But it doesn't matter how much material you place in there. You could put a meter of lead in there, you might still get a signal coming out the other side. And should I just say there that the signal, to detect it, the detector, is called a Geiger counter. Now, you might still be detecting something. So why would you still be detecting something? Well, you need to bear in mind that there is something called background radiation. And this means background radiation means it comes from natural sources all around us that we can't get rid of. Two very good examples of this are the sun, cosmic rays, and the rocks in the earth. Now, because you're always going to get a signal because of background radiation, when you're taking readings, you must correct for background. In other words, you take your reading and you minus your reading of the background. And the way that you find background radiation is you just leave the detector somewhere completely away from a radioactive source and let it just tick over for a long period of time. Once you've let it tick over for a long period of time, you need to work out its activity, and I suppose that's the next bit we need to bear in mind. The activity of a sample, because the background count will be given as the activity of the background. Okay, so the activity equals how many decays per second are happening. So let's just imagine I had 50 decays in a time of 5 seconds. Then my activity would be 50 over 5, 10 decays per second. What we do is we call that 10 becquerels. B-E-Q-U-E-R-E-L. Number of decays per second is given the term becquerels. Now, when you're dealing with radiation and you're trying to take a background count or any reading, because radiation is random, because the decays are random, always repeat readings. Always repeat your readings all the time. Okay. Two last things. What about the uses? All of those properties of radiation, alpha, beta, and gamma, make them very effective for certain uses. Alpha is a really good example of what you would use for a smoke detector. So you have the source and a detector, and this is a link to some electronics, and definitely a buzzer, along with other things. And because this is a constant stream of alpha particles going across and hitting the detector, the little internal computer here suggests that everything's okay. However, if smoke moves between those two, the source and the detector, then because smoke is so large, alpha is readily absorbed. And why is it readily absorbed? Well, because it's highly ionizing. And if smoke gets in the way, it stops the alpha from getting to the detector, and so the alarm sounds, which makes for a really good use. Okay, what about beta? Well, beta is really good because it can get through materials. So let's just imagine you had something like metal, you're making metal, you're pressing metal, and you want to press it just to the right thickness. And what you do again is you have a source and a detector, and you know that the metal will absorb some of the radiation coming through. Not all of it, but some of it. So if the detector senses too much radiation coming through, that must imply that this is too thin, because it hasn't absorbed enough, and so therefore these rollers move out. However, if it's not receiving enough, then that must suggest that this is too thick and absorbing too much of it, so the rollers will be squeezed in. So you have this instant feedback. The reason why alpha wouldn't work is alpha wouldn't get through at all, and the reason why gamma wouldn't work is because gamma would always get through if you have little absorption. Beta is also very good for tracers, because inside the human body you want to be able to work out what's going wrong in the body. You therefore want you want to get a radioactive source into the problem area of the body, and if it's into the problem area of the body, that's a massive arm there, as much as it gets there, you want the radiation to be able to get out to get to your detector. So therefore, if it were alpha, it wouldn't be able to get out. If it's beta, it does get out. Interestingly as well, gamma can get out as well and get to the detector, probably doing less damage. However, the one thing with tracers is you're interested in the timing. You don't want it lasting so long it's going to kill somebody. You don't want it so quick you can't get them into the machine. Tracers. In gamma, though it is weakly ionizing, it is very powerful, so you can kill all biological material with it, including bacteria. So let's imagine you had a pair of scissors or a hypodermic needle that you need to take into the operating theatre, and you wanted to make sure it was completely sterile. You seal it in a plastic bag, you put it, and you irradiate it with gamma. All the bacteria inside it dies, and when you next open it, it's very sterile. Fantastic. I suppose our last point, which I've sort of just raised there, was half-life. You have a radioactive sample. It's giving off radiation. Of course, the amount of radiation given off is proportional to the size. If you have something that's smaller, it gives off less. If it's larger, it gives off more. The amount it gives off is completely random, but it obeys statistically it's predictable. So though it's random, if you have a large enough sample, if large enough, then it's statistically predictable. So therefore, when you look at either, and it can be either here, over a period of time, it can either be the number remaining, the number of particles remaining, or it could be the amount given off, the activity. It always behaves as a curve. And that curve, whichever position you start with, let me say arbitrarily, so that's 200, this is 100, that's 50. Whenever you look to half of the starting value, that time will be the same irrespective of your start point. I can start from 100 and go to 50, and that time will still be the same. It's the nature of this type of graph, it's exponential. You don't need to know that, but that's the nature of the mathematics. So whatever starting point is, go to half of it, and that's the half-life of the material. Of course, you can get into some confusion with half-life, because let's imagine you had 50,000 atoms. That's a tiny number of atoms, but anyway, so 50,000 atoms. You knew the half-life was 10 years, and you wanted to know how long it took to get to 12,500 atoms. How long do you think that's going to take? Well, most people say, well, there's a jump of a quarter here. So if it's a quarter, it's 4 lots. Well, think about that. The time it takes. Each half-life halves the number of atoms. So that's one half-life. Then we get to 2,500. That's another half-life, which takes us to 1,250. So 2 half-lives gives us 20 years. So it's 20 years that takes us to that figure, not 4 lots, because you halve, then you halve again to get. Okay, so I'm just thinking if we've covered pretty much everything we have at high speed. We've talked about Rutherford model of the atom, notations, why things decay, the randomness of it, the radiation type, the uses of the radiation type, background, types, half-life. I think that gives you quite a lot to have a think about, and if I've missed anything out, I'll put it on another video.